Good afternoon, everyone. First of all, thank you for all being here. It's my big audience. My name is Malik. I think most of you knows me. I don't know if you have visitors or no online. So I'm a PhD student in the doctoral program, geotechnical, the geotechnical doctoral program. And today, more or less, I am presenting the work that I've been doing for my first year. So basically, today, I'm going to show you a method or a scheme to include biochemical reactions in Lagrangian models. What I mean by Lagrangian models is this type of models in which we formulate the problem using representative particles that spread or flow, which are the opposite of Eulerian models, in which we represent the solute as a pointwise concentration in space. I mean, this is a very, not very rigorous, I'll say, comparison between the two theories, but I think for the sake of presentation, it's fine. So yes, what we want to do is that to include biochemical reactions in Lagrangian model. This is the talk today for us. So why we are doing this, or why we are interested in modeling biochemical reactions in porous media? And actually, this is a very important question because I mean, it's not really clear if we can derive a model that can capture the details of reality. So here I tried to list some of applications in which numerical models can be useful. Here more or less more practical applications in which we can design or optimize remediation techniques. I think some of the people here are working on this kind of problems. Also, we can predict an outcome or scenarios that can take place if we excite or manipulate the natural system. But at the same time, we can understand, we can understand the complexity of a system using numerical models. For example, here we have like in contaminant aquifers. There are several processes that take place in different scales. For example, in the macro scale, we have dispersion, force, and attraction due to the heterogeneity of flow paths. And then in a pool scale, we have mass transfer, which usually modeled as mobile and immobile zones. And some people also will model it as a mass transfer in biofield. So explicitly, they will include biofield as an additional phase. And then in a lower scale, we have a mass transfer in the organism scale. We have the substrate or the contaminant can transfer to the plasma membranes or the cell membranes in the organism scale. And then in the molecular scale, we have the benzene catalyzed reactions. So I mean, with this picture, you can see that it's good to have a numerical model that can show the coupling of, or let's say, the effect of each of these processes. So what people have been doing in this direction, people have been using Eulerian models. Eulerian models which are based on Eulerian methods, let's say, which are based on attraction dispersion equations, in which they let's say, approximate or criticize or to approximate using finite element method, criticize. Which they criticize the stations in the finite element or finite volumes. They include biochemical reactions as monokinetics, which is this system over here. And in this kind of approach, I don't know, some people will disagree, but this kind of approach can be very challenging in case we have, let's say, high Piclet number, we have a medium dispersion, or or a high concentration gradients. I mean, if you're using a numerical code, of course, I mean, you give it the initial condition, the boundary condition, they will give you a solution. But these solutions, for sure, they can be smoothed. I mean, it's not guaranteed that you will capture the concentration gradients or the heterogeneity that you have. So we decided to work on a declarative approach, which is a Lagrangian. But then we have to find a way to include this ability, let's say, in a Lagrangian simulation. What we did? We did this to drive or write unknown kinetics as the two-step reactions. In the first step, we say that the biomass binds to the substrate and they form a biomass substrate complex. They form an intermediate complex. And in the substrate, they can, in the case of cellular respiration, they can be the electron donors or the electron receptors. And then in the next step, this intermediate complex dissociate and they give you a product and the initial biomass, and you have an additional biomass that represents the growth. This delta E. So this delta E can be computed with the yield coefficient for the people who are working on biochemical reactions. So if we apply the law of mass action on these two step reactions, we have this ODEs, a system of ODEs, and we say, okay, the intermediate complex is an assumption that's stable in time, so the derivative equals 0, we arrive to monad kinetics. We can derive monad kinetics. So the interesting thing about this is that we know how to simulate these two reactions. So when we decompose them, we know how to simulate them stochastically. And then we can include them in particle tracking codes. And in this derivation, it can be seen as an extension of Michaelis-Menten, which is another model, but Michaelis-Menten have a conservative enzyme, so the enzyme doesn't change in time, so you are not including the growth of biomass. So far, so good. And then I wanted to see, okay, so when we simulate these two reactions, how far we are from monad kinetics. So, or to say that in which cases this assumption is valid. So I tried to write it analytically, but I couldn't. So I brought the problem with the hammer. What they did is that I define two dimensionless numbers, and then I compare these two models numerically. I define a deviation, there's a deviation between the two models, and then I do a simulation basically, or I solve these equations numerically, and for different type of initial and parametric conditions. And from here we can see that there is a range of parameters in which these two models are the same, because you have a very low value of deviation, and in some parts, no, they deviate. So they are not the same. I mean, at least now we have a criteria that, okay, we simulate two-step reactions, we know if we are far from monad kinetics or not. And then, these numbers, these numbers I invented them. But we still decided to zero there. I mean, here, I'm sorry, here I'm not using the notations here. So the x is the p. So the x is the biomass. Okay? Okay, so I said one number is the biomass divided by the substrate, the concentration of biomass divided by the concentration of the substrate, divided by the yield coefficient. Okay. And you will find that it's dimensions, so we have dimensions. It's the same. And then what? And then you can say, okay, in this vision, the two models are the same. You can arrive to some criteria that tells you where you are. So far, so good. So now I've coded the model with MATLAB. This is more or less the summary. I mean, I'm using techniques that already developed in the group, so methods. I mean, basically what we are saying is that the total mass of each species is divided by a representative number of particles, and then the concentrations can be divided as can be obtained as the probability distribution of these particles. The particles will the diffusive or advective fluxes will be simulated by a random walk. And then for the reactions, we simulate them stochastically by computing the probability of the reaction. So in case, I mean, here's more or less the code. Each time step, I do a random walk, and then I do a kernel density estimation to obtain the support volume of each particle. And then in the first step, I compute the probability of the reaction, and I flip the coin. So if the probability is larger than a randomly generated number, so they react. I remove the particles and I include the product. If not, they stay there. I mean, and so these are the two reactions that they have in my model. What else? Yes.
See?
So this is a first example. Okay. Here, there's no mass, there's no transport. Here I'm comparing two batch systems between monod model. So I'm comparing these two equations. This system, here you have the biomass, this is the concentration of the substrate, and this is my food system. So I'm comparing them against the experimental data. I mean, you can see that both of them, they provide a very, very nice fit, actually. I don't know, I cannot believe it. I think the experimental data are quite good. Okay. So I'm using least square minimization. So this will be the obtained value, and this will be the experimental value. So I'm minimizing that function, which is an error between the model and the experimental data. And these are the values of this model. And more or less, they are quite well. I mean, I should explain the experiment. So, I mean, basically, it's a batching experiment in which the blue lines are the optical density of that putida F1, which is a microbe that's it's aerobic, so it's under aerobic condition. What else? And then they measure for phenol, benzene, and toluene. And in the second experiment, I modeled the degradation of carbon tetrachloride for a static column. So here there's no flow, so only diffusion. So what they did is that they built a 1D column and they filled it with sediment and groundwater. And then in day 0, they injected a denitrifying bacterium into this KC. And then they measured at different parts on the column the concentration of nitrate, the carbon tetrachloride, and the optical density of the bacteria. So I mean, this reaction has been studied in several papers. So I didn't go. So I just used the assumption that's been established before. I didn't go on the details of the reactions. And normally it's modeled in this way. So you have the degradation of carbon tetrachloride second order in time. Second order, yes, the reaction rates. And then the consumption of nitrate, it follows monod. So I use this assumption, I run my code, and these are my results. I mean, I managed to capture very well the degradation rate. I try to maintain, to use the same parameters that the ones that are obtained in batch systems. However, I mean, the biomass, I mean, I did, I don't know, 3 or 4 orders of magnitude more. However, they measured the let's say, the motile or the planktonic cells. So the cells which are swimming. Normally with this diaphragm, you have a biofilm that might form. Of course, I mean, they don't measure, they take samples of the water, they measure for the optical density. Which is to say, I'm not comparing the same things. Here I have the total biomass, and here I have the swimming one. I've tried to add the attachment and the attachment of biomass, which is something that people do, but the parameters are, I mean, it's not very clear whether you can tune these parameters with data that's there. So I mean, you can find the attachment rate of bacteria that can forms a biofilm, and then the attachment. It's not very clear, these parameters. What else? Yes, and I think by this I'm finished. Now I am trying to extend this for full-scale simulation. I wanted to talk about this, but I didn't have time to stay messy. Yes, so using the randomly generated medium, and we run simulations, yes, and we are trying to see how biofilm might form under different flow transport conditions. And with this, thank you. I try to be very quick with this. Questions?
I have one. When you talk about the attachment of the biomass, is it highly dependent on the velocity of the experiment? I mean, you are modeling like a batch experiment.
It's a first order. They model. It's a first order. So it's the first order like depending on the amount of bacteria that you have there, you have. I mean, it's a first order. No. It's a first order. Let's say for the change in the bacteria. Okay. Something like this. What is the value? They give it a value in the model, then maybe you can see that I can fit those and attached phase, so I can fit the mobile or the mobile phase that's still swimming in the column. But I don't know, I think like these parameters were taken. Very clear. Yes. And how do you select the value? Value kernel density estimation. Yeah, but the one of the other one I'm related for selecting the yes. Yes, the one that PM has been using, the toy, I think it's called whatever. It's there, it's in MATLAB, it's easy, you don't have to touch it. And this value was also a big parameter from the show that you were being nice about. I'm sorry, this is a batch system. Already in the batch system, I don't have particles, I don't have particles, I'm only comparing the two systems of what we use. Alright, then you're saying the reaction parameters. I'm sorry. No. So I am maybe I will explain to regard what I'm doing. That's right. Yes, what I'm doing is basically I'm comparing these two systems. These two systems. This is the monode, and this is what we use to simulate. So I'm comparing these two. And what we do is to work for that experiment. In the next slide, we have an initiation problem. Yes. That is to be nice to work. Okay, so just to find the best fit. So I have a model and then I have a data. I solve this problem, I get the best fit based on this criteria. Yes. Okay. More questions? No, I just want to say, describing with comparing two models, no? One with kinetic, and a linear, and a model. Yes. And for instance, here, what is what? Yeah. Yes, that's maybe not that. This is the concentration of toluene. The red is the organic compounds. The lines are more. Yes. They are identical. And they cannot see. You cannot see. So here maybe you can see a bit. One of them should be attached. And just another. I don't think about it. Yes, of course. Because you have two models. Yes, the model and the all have replicas and items. With the paper, we have another method similar. And I think it will be interesting to do something with, especially with the Lagrangian. Okay. Because here, for instance, I think Lagrangian will be very nice when you want to look at the mixing. Right now, we do a post-mixing. Already, post-mixing. Yes. And also, I guess, zones, very high. Exactly. Yes. More core with the concentration rate. Why the yes, also, especially for legal shows. Okay. But I mean, use. I know you're saying not approximately as a first one. Yeah. But you can also work. Yeah, I mean, I remember. I mean, no, but it's nice to have the videos. Yes. I mean, yes, actually, in the paper that I have here, they talk about this. And they say, you know, what I have here, yes, in this one, they talk about the little zone and how it's a big deal. Yeah. This is paper. I cannot pronounce it. So, yeah, little zone. Transfer then what's usually done. So I think that the videos on the going to make a very thin videos on. This is what they are. Yes. The typical picture where you have a strong acceptor. Yes. This is what they are. It's a very thin zone. This can be done very well with that. Yes, I think so. Yeah. Yeah. Okay. Someone else? I don't know that somebody